All right, let's go ahead and do the right endpoints now. Because it's right endpoints, I'm going to draw my little representation of right-sided bases. My rectangles here, since I want 4 of them, are again going to be calculated by taking this left end, or this endpoint here, minus this endpoint, so 2 minus 0 divided by 4 again, which reduces down to 1/2. So each one of my rectangles is 1/2 wide. This is still y equals 1/2 x squared. I'll go ahead and write that down. Okay, it is right endpoints this time. So I'm going to come all the way over here, and I'm going to draw my line going up to the function, and then over, and then down. Right side up to the function, over, and then down. Right side up to the function, over, and then down. Right side up to the function, over, and down. So this time we actually do have 4 rectangles with area. Last time we had this one with no area on it because it had no height. But this time this rectangle does have some height to it. Okay, all we got to do now is calculate the height of each one of these rectangles, and then multiply by the width, which was 1/2, and then add them all together to get our total area. So what is the height of this one right here? How would I calculate that? Plug the right endpoint of this rectangle into the equation. So we're plugging 1/2 in up here. 1/2 squared is 1/4 times 1/2 is 1/8. So that height is 1/8. Got it? Okay. This one, what are we plugging in? We're plugging 1 in because that's the right endpoint of this rectangle up to the function gives me the height. So we plug 1 in. 1 squared is 1 times 1/2 is 1/2. Notice anything? What's that? Yeah. So it's going to be the same numbers as we had over here, except for we don't have this one. We have this one starting first, and then this one. So the next one should be 9/8. Yeah. We plug in 3/2 up here. 3/2 squared is 9/4 times 1/2 is 9/8. So we do have this new rectangle over here with a height of 2. We take 2, plug it in. 2 squared is 4. 4 times 1/2 is 2. So the height of this one is 2. Now what do we do? Do we add all these together now? Could we?
No, we figure out the area.
Okay, you could figure out the area of each one. That's exactly what we did last time. Question is, can we add all these together now and then multiply times the width of the rectangle? No? If I took this rectangle and I stacked it on top of this rectangle, and I took this rectangle and stacked it on top of that one, and I took this one and I stacked it on top of that one, wouldn't the overall height be the sum of all 4 of these heights?
Yeah.
And then couldn't I then multiply that by the width 1/2? Yeah. So I could add all these together now and then multiply by 1/2. Basically what I'm doing is verbalizing the distributive property. Okay? Or I could multiply each one of these by 1/2 and then add them all together. It makes no difference. Because we're dealing with 8ths, halves, and 8ths here, maybe I want to do that instead. So I need a common denominator here of 8ths. And of course you could use your calculator, but we don't want to do that. So we have 1/8 plus 4/8 plus 9/8. 1 plus 4 plus 9, 14. And then this would be 16/8. So 14 plus 16 is 38. Is that my answer? Okay, that does reduce down to 15/4, but we have to multiply by 1/2 for the area. So we have 1/2 times 15/4 equals 15/8. So there's my area. Using right endpoints, which we know, based on the drawing that we have, is going to be a pretty big overestimate. So how could we make this not as much of an overestimate or an underestimate? Okay, so if we were to average the low and the high, we'd have 22/8, which would be 11/4. Divide by 2, right? Because we added two things together. So you'd have 11/8 as your answer. Is that a good answer? Should that be what we do? Is that a good sound mathematical thing to do? I don't know. What if I had something that looks like this? And then I use left endpoints. Left endpoints would be an underestimate, right? Okay, and so on. What if I used right endpoints? Right endpoints would be still an underestimate. So we'd just be averaging two underestimates then. Would that give us a more accurate? No. Use more rectangles. Yeah, that's what we need. So let's do it again. Except this time let's use 8. 8 is easier to use than 6, especially when I'm working with 2.
More accurate, because when you use the right endpoint, you know that you've accounted for all the areas.
Yeah.
But then left endpoint, you have like, I don't know, I just feel like right endpoint is more accurate.
That's a great question, and that's a great answer, actually, both of you. It depends on what you're working with. Do I want to have an overestimate? Is an overestimate okay? Is an underestimate better? In that case, looking at the graph and then deciding which one you would rather go with would be the better answer. Okay? Yeah, good idea. Okay, calculating the area using left endpoints, and this time I want to use 8 rectangles. So talk me through it. It's the exact same function still. Okay, so what would I write? 2 minus 0 divided by 8 rectangles this time gives me a width of 1/4 for each one of my rectangles. And the same thing is going to be true on this one over here when we use right endpoints. Okay? Now what should I do? Draw them in. Using left endpoints and 1/4 of a width, so we have, here's 0.5 right here, 0.1, 2, and a half is right there. And then 0.5, there's one, and then there's another one, there's one, there's another one. Okay, does that give me 8 rectangles? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Using left endpoints, I'm going to change color so we can see it more easily. From 0, we're going to go up nowhere, and then come over, and then down. From here, 0.25, over and down. From 0.5, up, over, and down, and so on. You get the idea, but I'm just going to draw these in here anyway. Okay, so clearly still an underestimate, but if I go back, I'm definitely not wasting as much space. Okay? Okay. Now what?
Now we find the height first.
Okay, what should I do?
Plug in the
Draw the little things to show me that I'm using left. It's just a trick to help you get through the problem. You don't have to do it, I suppose, but it does help, I think. Okay, now what?
Now we find the height.
Now find the heights. So this one here would be 0. Okay, next one. 1/4 squared. 1/16. So 1/32. Okay, next one. True. So it's 1/2 squared, 1/4 times 1/2 is 1/8. Next. So what's the left endpoint? 3/4. Squared is 9/16. So we get, okay, 9/32. All right, next one. 9/8. Because it's 1 squared is 1 times 1/2 is apparently 9/8. Okay, this is 1.25, so that would be 5/4. Yep. 25, 30 seconds. Okay, next. 1.5. 9/4 times 1/2 is, here's your 9/8. And finally, 1.75, so 1 3/4, 7/4, 49 sixteenths times 1/2 is 49, 30 seconds. Yeah, okay, but now we have all the heights, right? So we have two options. Multiply all of these by the width and then add them all together. Or add them now and then multiply by the width. Add up all the heights and then multiply times the width, that's right. So common denominator here, 30 seconds, right? You want to write them all down or you want to do it in your head? Do it in your head? If you were able to use a calculator, you would use a calculator here. If you're not able to use a calculator, can you do this? I know y'all can. So we have 1 30-second plus 4 30-seconds, so we're at 5, plus 9, so we're at 14, plus 16, so we're at 30, plus 25, 55, plus 36, so we're at 55 plus 36, 91, plus 49. 140, 30 seconds. But we're going to reduce that. (35/8) times 1/4, which is 35 30 seconds. There's your answer. So it's not too tough without a calculator, right? It's not too bad. Actually, I kind of think that we did that faster than we would have if we typed in 1 divided by 32 plus 1 divided by 8 plus. It does take a little bit, so we're not that far behind. Talk me through right endpoints. It's the same width for rectangles. Each rectangle is 1/4 wide. So I'm going to mark those on here. 1, 2, 3, 4, 5, 6, 7, and then there's 8. Now what?
Now right side, up to the top, over, down.
Start on the right side, up.
Up, over.
Doing my best to draw this straight for you guys. Over and down. I know you do. Over and down. Over. Apparently my shoulder's not operating correctly today. Over and down, over, down, over, down, over, down. There is a little bit of area on that last rectangle this time. So let me bounce back again just to show you how much less space look at how much less of an overestimate this is going to be. So go back, now what?
All right, well, let's make our little right thing. Backwards.
The right side of the bases of our rectangle is what's being drawn here, not little backwards L's. Next.
Well, we just kind of shift like we did in the last one. Some of them.
Pretend we don't know.
Let's take the numbers and push them.
If this was a quiz, and I just asked you for the right endpoints of this situation here, not the left endpoints, you wouldn't have any of these numbers sitting here.
Okay, well then we plug it in again.
Right. So what do I get here? What do I get here? It's 1 32nd. What's going to be here? 9/8? 1/8. And here, 9:30 seconds. And here, 1/2. And here, and here, and here.
49:30 seconds. Now we just have to figure. Yeah, but we just have to figure out one.
Oh, we have to do an extra one. No,
8, 2.
I can't do that.
All the
We've already figured it out like 3 times.
it goes all the way up to
It goes to 2
2 squared.
is 4 divided by 2 is 2. Okay, so what is our answer going to be?
Well, let's add those all together.
Add them all together? Okay. Go ahead. It's what we have plus 64:30 seconds. 35/8 plus 16/8 would be 51/8 times 1/4. 51:30 seconds. So this is 1/4 times the 51/8 that you just came up with. 51/8 equals that. So there's your area using right endpoints. All right, find the sum of all the integers from 1 to 100. We know that all we need to do, actually let me cover all that stuff up so we're not staring at it here for a second. We know that all we need to do is write down 1, 2, 3, and so on up to 100. Repeat that 2, 3 the other way, and then 98, 99, 100. Add them all together. We get 101 each time, and so on. There's 100 101s, so we go 100 times 101, but then we added them together twice, so we divide everything by 2, and we get an answer of 50/50. What just happened there, let me clear that off there and then move this thing back out of the way, is summations. And that's what the other half of this section is about. Your sigma notation, this is your Greek letter sigma right here. It's the shorthand way of expressing a summation of terms, which is what we just did. We added together 100 terms. The shorthand way of writing that would have been to use sigma notation. The key parts of the sigma notation are this guy right here. This is your index. This guy right here is how far you're going, how many terms you're counting up. And then this right here is your function, or whatever the rule is that generates each sequential term that you are adding together. So when I equals 1, we have a sub 1, and that's our first term right there. Then I goes up by 1, so I becomes 2. Now we have a sub 2, so we put that there. Then I goes up by 1 more to 3, and that gives us a sub 3. And then I goes up to 4, and we plug 4 in right there and simplify it down, and we get a sub 4. And we keep going until we get to when I equals this number right here. So we keep counting until we get to that number, whatever it is. Substitute that number in, simplify it down, and that gives us that last term right there. Then we add all these things together, and we have our total sum. And that's what all this stuff right here is. The index of summation is I. The ith term is a sub I. The lower bound of summation is whatever I is equal to under the sigma. So in this case, I is equal to 1. That would be your lower bound. Notice the vocabulary there. I'm pretty sure I've used that phrase before. Upper bound of the summation is n. That's this guy right here. That's where you stop. This is where you start. This is where you stop. The lower bound can be anything less than the upper bound. Typically it's 0 or 1, but most of the time, at least in this class, we'll be working with a lower bound of like 0 or 1. But it can be anything that's less than that n. Both bounds have to be a constant. The only thing that can change is the index. And the index must stay between the lower and upper bounds. So the index changes each time you generate your next term. The next goes up by 1. So the index is always between the lower bound and the upper bound. So, some examples of how to use summation notation. They're all fairly, well, they get more complicated as we go, but here's the idea. We have a lower bound of 1 and we have an upper bound of 6. So we're starting at 1 and we're counting until we get to I equals 6. So and it's just of I. So that means that I take my index, 1, and I plug it in for I, and I just have 1 sitting there. So that's my term, 1. Then this increases by 1, so from 1 to 2. And then I take 2 and I plug it in right there, I just get 2. So now I have plus 2, and I repeat that process. This becomes 3, plug in 3 right there, simplify it down, there's no simplifying to do, so it just is 3. All the way until we get to I equals 6. So we get 6 there, and then we add all those numbers together, 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we get 21. This is a fairly basic problem, and the lower bound and the upper bound are fairly close together. We just have I sitting there, so a lot of the times when you get a problem like this, just do it by hand. You don't have to worry about any sort of formula or anything like that. On this one, the big difference is this time we're starting at an index of 0. So the lower bound here is 0. We take 0 and plug it in. 0 plus 1 is 1. And so we write down 1. Then this changes to 1. 1 plus 1 is 2. And so we write that down. And so on. Notice that we wind up with exactly the same result because the upper bound here, I changed it to 5. The upper bound here could have been 6. It could have been anything, but it happens to be 5. So when I is 5, we get 5 plus 1, which is 6. Write it down, find our sum. On the next one, we're using the letter J this time, and we're starting at 3 for some reason. It's no big deal. We take 3, plug it in, 3 squared, write it down, plus, this is now 4. 4 squared, write it down, plus, this is now 5. 5 squared, and so on until we get to J equals 7, our upper bound here. We write that down, and then we simplify that, and we add them all together, and we get 135. More complicated this time, we're using K, starting at 1 and going to N. So different than before, we had a number up here. Now we're just going to some number. I don't know what the number is. And my equation or expression sitting here that I'm using to generate each term has N involved in it, and it has K involved in it. I'm plugging in 1 for K, not for N, for K. And I get 1 squared, which is 1, plus 1 is 2. So this simplifies down to 1 over N times 2. Basically, that's what I have sitting right there. Now we change the number to 2. So we plug 2 in for K, and now we have a 2 sitting right there. We still have that 1 over N times 2 squared plus 1. And we do the same thing for this one. And now I can't show you every single term because I have no idea how far we're supposed to go. But I can show you the last term, 1 over N times N squared plus 1. Then we would multiply all that out, simplify it down, and get our answer. Finally, the last one, I equals 1 to N. So instead of K, we're back to I, but we're still going just to N. And this time I have some sort of function sitting here that's listed as a function of X. And then I have this sub I. And then I have a times delta X. So quickly we're getting back into calculus here. When I is 1, we'd have f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x, and so on. Each one of these delta x's is exactly the same. I'm not doing anything to it. Each one of these sub i's right here, x sub I, tells me that when I plug in 1, I'm getting x sub 1. When I plug in 2, I'm getting x sub 2. When I plug in 3, I'm getting x sub 3. Each one of those would be like an x coordinate that I'm plugging into my function, whatever it happens to be. This is just function notation here. Whatever my function is, I'm plugging that x sub 1, x sub 2 into my function to get basically like the height of the function, okay, times the delta x, which we were just doing on those rectangles. Okay, any variable can be used for the index of summation, so you'll notice that I switched from I to J to K. You can use I and J and K typically, but they could be anything. It could be an M, an O, a P, whatever you want. Generally though, you're going to see I, J, and K, and most of the time in this class, you're going to see I. All right, notation out of the way. We have a couple of important properties of summation that we need to talk about. Notice the notation that's sitting here. We have I equals 1 to n of k. What is k probably? A constant. And then we have some term sub our index, so a sub I. The property is you can take that constant out, just like we've been doing all year long with everything. That constant can come out front, and then you have the sum from I equals 1 to n of just the a sub I. The other property we need to talk about, same notation here, I equals 1 to n, but this time we are summing, I should probably put parentheses around those, something plus or minus something else. We can split that summation into two separate summations. I equals 1 to n of a sub I, and then plus or minus I equals 1 to n of b sub I. So just like we have been doing all year long, we can apply the sum to each individual term on its own. So going back to the original question, the sum of all the integers from 1 to 100, how can I write that using sigma notation? Well, obviously I'm going to have this, and you said n is 100, so I'm going to put 100 there. I is 1, so I equals 1, and what am I doing? So what should I write next to that sigma? How about just I? Because when I is 1, then we have 1. When I is 2, then we have 2. And we have 1 plus 2, and then plus 3, and then plus 4. Okay? So that's the answer. What if we wanted the general form in sigma notation for the sum of all integers from 1 to any number? Nope. We're still going to have sigma. We're still starting at 1, right? It says from I equals 1 to any number to n of just I. Yeah. So now we can add up any number we want starting at 1 using this notation. Common summation formulas. These things pretty much need to be memorized. Yeah, good stuff for sure. The first one, the sum from I equals 1 to n of c. C is just a constant. Notice that I don't have anywhere to plug I here. So I is 1, we just get c. I is 2, we just get plus another c. I is 3, we just get plus another c. So we're just going to have this long line of c's being added together. How many c's do I have added together here? N of them. So that's why this reduces down to just c times n. This one over here, I equals 1 to n of just I. This is the add up all the numbers from 1 to 100 situation. We wound up with 100 times 101 divided by 2. And you guys developed that one all on your own. It didn't take very long at all. So this one's going to get used a lot. I equals 1 to n of just I is equal to n times n plus 1 divided by 2. So the first one was logically obvious. The second one you guys developed kind of on your own. The third one and the fourth one, you're going to have to take my word for it. There is a way to develop those. There's a way to prove that those are correct, but we're not going to learn how to do that in this class. I think the book might actually have an explanation if you look in the book on how those come about. But if you have I equals 1 to n of I squared, then this converts to this. And basically that's what we're doing here, is we are converting from summation notation to a way to algebraically find the sum easily. This one comes up a lot. You need to have that one memorized. And finally, the last one from I equals 1 to n of I to the third this time becomes this one right here, n squared times n plus 1 squared, all divided by 4. Come up with a way to have those memorized. They are important.